Hello my friends, welcome again to my video channel. Today I will start a new project, Braun LT470. It's a linear transverter from 2 meter VHF band up into the 70 centimeter band UHF from 144 to 430 megahertz. It's the companion transverter to the Braun SE400, to the 2 meter transceiver. I made a series of videos about it when I got it and I repaired it. And in the last time I was looking for such a transverter, I was lucky to find one at a reasonable price. Sometimes prices are beyond any discussion, but this was a very reasonable price. There's maybe one problem. The owner told me he couldn't get it working. He was not able to get out a signal in the transmit path. On the other hand, he had no transceiver as it was necessary. So maybe there was a problem with the operating of the push buttons and the correct wiring. There's a special control cable needed to connect this transverter to the transceiver. So maybe it's an easy project when there is no big fault, but I will do a complete realignment. Maybe we have a bigger project when there is a fault or some faults. So let's start. This transceiver is optically in nearly perfect condition, in mint condition. It's a famous Braun design, but it's a different company, as I've said in my videos about the transceiver. This company Braun has nothing to do with the company Braun who made the stereo receivers, radios, TV sets and so on. Two different companies, but the design is very similar. Maybe if there was a sort of cooperation or any influence. Here we have only the alternator for the 2 meter input. This transceiver accepts, as I know, full 10 watt input power. The power can be attenuated here. That's the output of the RX part of the converter from 430 to 144 megahertz. And here we have some push buttons to control it. Here we can choose the frequency range for 32, 34, 36, and this is for relay operation, or better said, repeater operation. There's a repeater shift inside, and this is for the inverse operation. And here we can choose in which mode we operate. 70-70 means RX and TX in both in the UHF band. 2.2 means both in the VHF band. That means this transverter is not operative. 72 means RX in 70 centimeter, transmit in 2 meter. This is vice versa. And this is on off. When it is off, the antenna is fed through. Here we have the antennas, 2 meter TRX. This is a connection for the transceiver, and this is for the 2 meter antenna. When this unit is switched off, then both are connected and the signal is fed through. Here we have the 70 centimeter antenna. This is a control cable. It's a 5-pin DIN plug, but we only need 3 pins. This is simply a changeover contact from a relay in the transceiver, which switches between RX and TX. And the center pin is on 2, and pin 1 and pin 3 is changed over to 20 volt power supply. That's it. As I said, in nearly mint condition, and inside it's also very good. I've seen it. But first I will do some tests to see what happens, whether it's really not working or whether there's a problem on the operator side. The whole combination is set up, is wired. I have here the 3-pole control cable, homemade. There is the antenna cable from the 2 meter transceiver to the output of the transverter or input. And here we have the connection to the signal generator. It's a 145 megahertz signal. This unit is switched off. And as expected, we can hear the signal from the signal generator. It is a .3 microvolt signal. You can switch it off and on, so we are sure it's the right signal. This means in this mode the transverter operates. Then I will go to the on-off, and the mode is 2-2. That means receive and transmit on 2 meter. Same result, you still can hear the signal. When I go to 70-70 for example, okay, the signal disappears, and now I obviously have the input of the down converter. Okay, with the RX gain I can adjust it. 72 is the same, I could transmit on 2 meter. This is 270, that's also okay. I can receive the 2 meter signal, would transmit on 70 centimeter. But this is obviously all okay. And now I will try to transmit on 2 meter with very low power connected to my spectrum analyzer and see what happens, whether this is okay. But before I check the transmit path, I will check the receive path on 70 centimeter to see whether the LO, the local oscillator, is operating or not. I feed in a signal 432 megahertz, 434 megahertz from the generator, approximately 1 microvolt. The range is 432 to 434, so I have to tune the transceiver to 146, and here we can hear it. Maybe we can hear some frequency variations, some wow or so. This could be caused by the generator. I have a problem in the generator. I know it's not a. There's a problem in the relay switching between FM and so on, but not important. We can hear it with RX gain. We can set the sensitivity, and when I go to the range 434, 436, it's necessary to align the transceiver 2 megahertz down. I will do it. It's a coarse tuning. Oh. Frequency error of 26 kilohertz. Needs realignment. The generator is still locked. We have something to do. Next check is 436. I will set the generator to 436 megahertz. Generator is set to 436. Okay, we are spot on frequency. That's also okay. So the RX path seems to work. Some alignment is obviously necessary, but in general the LO operate. We are on the mode 70-70, and now I will check the transmit path. Now the mode 2 meter transmit and 2 meter receive, 2-2. Mode is FM. Here we have the analyzer. Top line is 10 watt. I reduce the power a little bit. When I go in mode FM to send, that means transmit, we have output. You can see it on the analyzer. Or to call. When I go to the mode 72, this would mean reception on 70 centimeter, transmit on 2 meter. I hear the relay clicking and it works. Okay, and now the next check is transmit on 70 centimeter to have a look at the output. I have to connect the attenuator to the 70 centimeter antenna. And now the same check on the 70 centimeter band. I have the mode 7070, that means transmit and receive on 70 centimeter UHF band. Mode is FM. The attenuator is connected to the BNC, to the 70 centimeter antenna. And when I go to to send, this is the input. We can see in the analyzer output signal up to 10 watt. The meter here, can't see it. The meter here also indicates 10 watt. I will show it a little bit in a better resolution. But we have output up to 10 watt in FM. When you use the call, we see the signal, and this analyzer is a little bit broader due to the modulation. Yes. But in general we have output. Let's check 270 mode, receive on 2 meter, transmit on 70. Same result. Obviously it works. There's some realignment necessary, of course, but in general this transceiver is transverter. Sorry, this transceiver is also okay, but this transverter here, in general, it works. Maybe the OEM had a problem with the control cable. He had no control cable, and to get it into the transmit mode, it's necessary to connect one of the pins to ground to activate the relays. The relays, the RX-TX relay, and to transmit. Otherwise it's not possible to transmit. Okay, next step will be I have to open it, look for some alignment points. Maybe the frequencies have to be aligned from the local oscillator. One has an offset of 20 kilohertz. That's ugly, so I have to check it. But before we start to have a look inside the transverter, we have a look at the block diagram. It's a rather standard diagram. We have here the 2 meter antenna and the 2 meter station. When the whole transverter is switched off, we have here direct connection 2 meter antenna to the 2 meter station. When the transverter is active, in case of receive, we have the input here, 433 megahertz. Here we have a 288 megahertz signal. It's created by a quintupler. We have oscillators with 57, 58 megahertz times 5. It's 288, which is generated here, and the difference 144 megahertz goes into the station in case of receive. That's the receive path. In case of transmit, the 2 meter signal is attenuated. It's a combo of some resistors, power resistors. Here we have a very variable amplification, and the 145 signal is mixed with 230 megahertz. This is a quadrupler. This frequency times 4 generates 230 megahertz, and there is still something missing, because 230 and 145 is 370, but we need a little bit more than 375, so we have another mixer. So the output is now 433 megahertz. It is amplified, driver, PA, and that's the output. And here we have the crystals for the frequency ranges and also for the repeater operation, which are selected by a matrix. This is a rather simple circuit, standard. The double mixture here is done with this and this, I think, to attenuate unwanted signals, because when we would have here only one mixing, then I think we would have a harmonic 3 times this frequency is also 433. This is not nice, so there are 2 stages behind to attenuate this effect or to reduce it. The chassis is out of the housing. First look on the bottom side. It's a power supply, transformer, rectifier, filter caps. This is a set of contacts to the relay for RX and TX, voltage stabilizer here and here. And this is the power supply, 220 or 230 volt. It's also shielded with feed-through capacitors, additional filters. It's an extremely good construction. And on the other side, where the high frequency parts are, I have very seldom seen such a construction. Absolutely perfect in my opinion. The engineers in those days did a very good work. We have here the input resistors, the attenuation of the 2 meter signal. We have here the 2 meter connection antenna and transceiver. That's the input, that's the relay, antenna relay. Here we have the input. This big resistor here is not necessary to be such big. It's only the resistor for the small lamp here. It has 180 ohms, a little bit too big. Maybe there was no other resistor on stock. And here we have the HF units. Let's have a little bit closer look at it. This part is the RX part for 433 MHz input circuit, input transistor, 2 filters. This is the antenna connection, which comes from the PA, from the antenna relay. This part here is the local oscillator with the 5 crystals, the 57 MHz. This here is the quintupler and the mixer. And this is the output of the 145 MHz, which goes to the switching to the relay. Here we have the local oscillator. This is the frequency doubler, as I see. Sorry, this is TX in, 145 MHz in. Yes, and this is a quadrupler, correct. And here we have the mixer and the 435 MHz first amplifier section. This is here. This is the driver, 435 MHz, and this is a PA. So here we have the complete HF part, up converter, down converter, local oscillator. Everything is built in here in chambers. Perfect construction. And as I see, there was nobody in before. All cores here are sealed, and as I see, originally sealed. Nobody tampered with it, nobody tried to improve or realign it. The trimmers here, I don't see in the slots any signs of scratches or so. This coil is also perfect. No signs that there were any attempts to improve something. It is in the original state, so I'm just thinking about whether it's really necessary to have a realignment. I'm quite sure it is not necessary, except the problem with one of the crystals here, where we have a frequency offset of more than 20 kilohertz. There seems to be something wrong. I have to look at it. That will be the next step, to check the oscillators, what's going on there. Here we have the power amplifier. That's the output, that's the antenna, output and input, heatsink. And this here is a connection from the relay to the input, where we have the RX path. Still, it's a perfect construction. It was very expensive even in those days. It was built, as I know, in the late 70s, early 80s, maybe until mid of 80s or so. Don't know exactly. I couldn't find any timestamp in it, any date of manufacture or so, only the serial number, but I cannot read it. 50, 57, it's not a year or so. Anyhow, very good, very solid construction, and only a problem here in the oscillators. I will try to identify the problem. Maybe one of the switching diodes, there are switching diodes for the 5 oscillators. The oscillators are aligned with these coils, not with trim caps. The coils are the decisive components to adjust the frequency. Maybe we have a problem with the electronic switching. There are switching diodes in it or in the output stage. Well, next step for me will be to check the frequency, to look into the alignment procedure, how to set the frequencies, and maybe we can identify the problem. To check the correct operation of the switching of the 5 frequencies, 5 oscillators, or 5 crystals, not oscillators, we will check the switching voltages. They are connected to ground to switch on the selected frequency. This is done here with this resistors and this matrix. Here we have a common plus which comes out from the emitter of this transistor. The base is set to a voltage of it is 12 volt, and here we have a common voltage. I think it's 18 volt or so, but this driving voltage is stabilized, and then the cathode of the diodes are conductive, or the diodes are conductive by connecting the cathode via this resistor to ground. So this crystal of this is selected. It's a simple matrix. We can check for the first, check the voltages here, measure the voltages, whether they are connected to ground, relay, and the various frequencies. These are the inputs. These pin row, sorry, a little bit less. These are the inputs. This is the sequence. C is the input of the control voltage, and one of the pins has to be connected to ground for relay or relay operation or repeater. This is a band for 436 to 438 and so on. And with the voltage meter, now I can check these voltages. First to measure C, this is input voltage, it's 18 volt. And the first one is for relay inverse. When I go to relay inverse, this knob, it goes down to 0. The next one is 432, 434. Next one is 434, 436. It's also okay. This one is 432, 434, sorry, 436, 438. That's it. And this one is for relay or repeater operation, and this one was for repeater inverse. The others. Sorry, this one. This is inverse. That's correct. So these voltages are all correct. They are measured as they should be. Next step we can do now is a check of the voltages at the diodes, at the cathodes, for example, whether they go low on the cathode when the cathode is connected to ground via resistor. I don't have the layout drawing for the oscillator here, but we see here the 5 blue diodes, the switching diodes, and the cathodes are marked. So I will check simply at which frequency range the cathode goes down and measure the voltages and compare the voltages for all 5 diodes. They should be nearly identical. So I start with the first one. I should connect the ground first. No ground, no measurement. And now the first one, 18 volt. And when I select the next one, this is relay inverse, goes down to 10. And when I select another one, okay, that means 10.4 volt. Next diode. It's not the cathode, it was the anode, sorry. $18 volt, 10.4 volt at relay. Then the next is 18 volt, 10 volt at 432. Okay. 436, 10.4. I think this was a frequency range where we had a problem. And then the last one, .436, okay, but we see it's always 10.4 volt when the diodes are switched. So as I see, the switching diodes and the resistors and so on are also okay in this network. So the problem indeed is not the switching circuit itself and the diodes. We only have one oscillating transistor in the center. So the problem can be only in the coils, in the alignment coils, or in the crystals itself. For this purpose I will measure now the frequency. Here is a test point. I will connect the counter and then I select the 5 oscillators of the 5 frequencies and see where the problem is. The counter is connected to the jack point M3. This is a fundamental frequency, 5.8 or 5.7 dot something. We can measure the frequency in the background. Now I will focus on the counter. In the range relay, I have here the frequency table. In the manual, relay has 5.8.800. I'm on relay 5.8.799. It's 800, 700 hertz. Okay, not so. But please note this frequency error is times 5 on 432 because this frequency is quintupled. Then this means any error here is times 5 on the UHF band. We can align it maybe relay inverse. The frequency should be 57.280. We can live with it. 432 to 434 should be 57.600. Is also okay. Now we come to the range 434 to 436. Should be 58.0. We are 57.995. We are 5 kilohertz too low. Times 5, that's an error of 25 kilohertz. That's exactly the error we have measured in the UHF band with the signal generator. We were 5 kilohertz above the frequency. This is the reason. This oscillator here is 5 kilohertz wrong. I don't know why. Next band is 436, 438. Should be 58.400. Okay, 3999. That's also okay. So this frequency is obviously wrong by 5 kilohertz. Now what's the reason? Could be a problem of the crystal. I will do some mechanical tests. First I will check which coil it is, and then I will a little bit tap on it, move it around. Maybe a bad solder connection could happen, or simply a realignment is necessary, but I've never seen that such an alignment drifts away 5 kilohertz. It's a little bit surprising. First I will do a mechanical test. According to the manual and the schematic, L14 is a bad guy and the crystal in the corner here. So I will tap on it and see what happens, whether there is anything which causes a frequency jump, or maybe I will tap a little bit on the crystal, move it around, nothing happens. You see the frequency in the background, can you see it? A little bit difficult with my hand. Not the best position for the camera, but when I tap it around, nothing happens. I'm tapping onto the diodes, nothing. But the diodes, the switching diodes are okay, as we have seen. The characteristic, they are switching as they should. So the problem can only be inside. I will open the wax and try to realign it. To remove the wax, I will use such a dentist tool that's perfect for this purpose. To scratch it. The wax is out, and now we see the problem. The alignment range is not good enough. I can only go up to 57.996, and even when I take out the core completely, the frequency does not increase. And when I go down and reduce the frequency, I can go down, and if you see now, the frequency will drop. When the core is in the coil, 995, 994, 993, I can go down but not up. What's the problem? Could be a problem of the crystal itself, or the problem was from the beginning, and the guy who did the alignment didn't say, because he thought the frequency range 434 to 436 is not so important, because SSB range is 432 to 434, and this is okay. This would be this frequency. If this is 57.600, this is okay, and also the relays are okay in the frequency range 434, 436. Now we have here an error of 4 kHz times 5, and the error is 20 kHz in the UHF band. It's a lot. The next step is to get access to the bottom side of this unit. I had to unscrew 4 screws, unsolder this wire. This is the output from the driver to the PA. Then I can flip it out, and now we have a side on the bottom side. Same construction, very precise, best quality. And here we have the resonator and the inductor, the left side, top left side. This is the coil, the alignment where we have the problem. I tried to simply make a bridge over this inductor to reduce the inductivity to 0, and then the frequency of the crystal should shift up to more than 58.0 megahertz, some kilohertz up. This would be an indication that it would be helpful to reduce the inductivity. Before we start to make a short or bridge this inductor here, we should understand what's going on there. The crystal with a frequency of 58 megahertz is most probably a third overtone crystal, not a fundamental frequency. It's a third, maybe a fifth, but I think it's a third overtone. How to get a crystal oscillating in the third overtone? Well, it's necessary to have a resonance circuit. We have a 10 picofarad. A little bit more precise. We have a 10 picofarad, and this is in series when this diode is switched on with this inductor. And this is a resonant circuit in the range of 58 megahertz. I can try to increase the frequency a little bit by decreasing this inductivity, but when I decrease the inductivity too much, then the oscillation stops. So it's difficult to find the correct point. I will try different coils. I will switch them in parallel to reduce this inductivity. It makes no sense to take it out and replace it by a new one, but switching parallel has the same effect. So I will try whether it's possible to shift up this fundamental frequency based on 58 megahertz by 5 kilohertz. I did several tests. This is an option. I have here an inductivity on a ferrite bead, 2 turns, and with this inductor in parallel, with this inductivity in parallel to the coil, the oscillation stops. This is too much parallel burden. I had a first attempt with 1 turn more through this ferrite bead. Then I couldn't reduce the inductivity to get it oscillating on 58 megahertz without error. This step here was a step too much, so I have no oscillation, and I cannot align it with the coil in parallel with the core. Even when I take in the core fully, this inductivity is too low, so it is very difficult, and I think it cannot be done. This is a problem. Obviously the crystal drifted too far away from the specification due to aging or so, I don't know. So I have to decide what to do now. I have here an inductivity meter for very, very low inductivities. I set it to 0, and this inductivity I've chosen has 3.3 microhenry. This is in line with the AL value of this core, which is approximately 1 microhenry or so. And I have 2 turns, that means 4 times. This is okay, but this inductivity is too small. It stopped the oscillation. I calculated the inductivities here when I chose the 10 picofarad in series, which we have here. So I need an inductivity of approximately 1 microhenry, 0.8 microhenry to be more precise, to get this in resonance for 58 megahertz. And when I switch the additional 3 microhenry parallel, this is a too heavy load, and the oscillation stops. Okay, this is also a question of the Tangens delta, of the quality of this ferrite bead. But in general, it seems that it's not possible to shift the crystal into the required resonance frequency. I take the core out as far as possible. Now I have an error of 4 kilohertz times 5. It's an error of 20 kilohertz in the frequency range of 434 to 436. I had a look into the band plan, and I found that there is nothing which is important for me. Digital audio TV, bandwidth 2 megahertz. Then something else with digital broadband units, digital voice, and so all things I cannot do with this transceiver and transverter combo. So I simply leave it as it is. I don't think about it. I will realign the other coils for precision where necessary to squeeze out the last 100 hertz. But that's it, what I will do, and not more in the moment. I keep it in mind that I need a crystal with 58 megahertz. They are on the market, I've seen, but I don't know the exact specification, what is required here. So I will have to try it. But in the moment, I will take my time for other projects, because other projects are waiting, so I stop it here now, leave it as it is, and I'm quite happy with it. Now we are at the end of this little project about the Braun Lineartransverter LT470. There was not a lot of work to do. To be more clear, nothing except the bad crystal. I have to look for a substitute. First check the characteristic, but it's not the main topic for me at the moment. Other projects are waiting, are in the pipeline, so this transverter can be used now, and I will use it on UHF. Stay tuned, stay healthy, see you on this channel.